Third classification, ferromagnetic substances. So those substances which are very, very strongly magnetized in the direction of external magnetic field. So strongly that even the external field is 1 Tesla, it can make that magnetic field go to 100 Tesla, or very strongly magnetized in the direction of external magnetic field. And we also, I think, discussed the Meissner effect. Did we? Radha, what is Meissner effect? ऐसा कुछ किया था हमने? Did I
No,
use
sir.
the word Meissner effect?
So no, the word was not there in my notes.
The word was not there. Okay, okay, fine. So that part is left. We'll discuss it in the end after the ferromagnetic. So ferromagnetic properties are similar to paramagnetic, but 1,000 times magnified. So paramagnetic was slightly magnetized in the direction of external field, and ferromagnetic are very, very, very strongly magnetized in the direction of external magnetic field. But there is only specific type of elements and materials which exhibit ferromagnetic material property, ferromagnetism, because of the specific geometry associated with this crystal structure. Like example, iron, cobalt, nickel, and their alloys. These are the ferromagnetic substances. So the reason, how do we explain that it is why it is only in these particular atoms, plus why it is very, 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 very strong. I mean, external field is 1 Tesla, it can make that magnetic field go to 100 Tesla by that magnetization. So the reason for the ferromagnetism or ferromagnetic behavior is these specific materials have some similar type of geometry. So one particular position of the electrons or atoms of inside the crystal will always be oriented in one fixed direction, and they have already formed a very high dipole moment. Again, iron, cobalt, nickel, and other d block elements, they have some metallic crystals. Their crystal structure you might have done in solid state. So body centered, face centered, and there are many other type of possible geometries for any solid state material. So one particular location, maybe some tetrahedral void or some corner, some face center, their electrons, those atoms are already pre-oriented in certain direction, so that the group of 10 to the power 9 to 10 to the power 11 atoms, their domains are already, their dipole moments are already in the same direction, and this group of atom is called domain. So domain is not an individual molecule. Domain is a group of atom, 10 to the power 9 to 10 to the power 11 atoms, and they have their dipole moment in one certain fixed direction. So there are such many domains, but their domains are initially free to orient in any random direction. Domains are oriented in any random direction, which is such that the electrons have random velocity in all the directions. Likewise, here also they have certain specific, certain number of domains, but their dipole moments, individual domains have very high dipole moments, but in this overall material, these dipole moments cancel out each other. Understood the concept?
Yes, sir.
Why there's a domain in this formation? Because of the specific crystal lattice. Because all the metals have certain type of crystal, but only these metals have some specific orientation, so that the electrons are not randomly. Each electron, some 10 to the power 9 to 10 to the power 11 electrons are already pre-oriented in the same direction, called as domain. Each domain has certain very high magnetic moment, but all the domains, they random, because of their random orientation, their net dipole moment becomes 0. So if we check their net dipole moment, in absence of external magnetic field, the domains are, what is domain?
So a group of 10 to the power 9 to 10 to the power 11 atoms oriented in the same direction.
Yes, having the same direction of dipole. In absence of external magnetic field, the domains are randomly oriented. The domains are randomly oriented and net dipole moment will be zero. Net dipole moment will be zero. That means there is no magnetic behavior, even though it is a strongly magnetized material. It will be very strongly magnetized, but if there is no external field, there will not be any magnetization. These domains dipole moment will also cancel out each other, and net dipole moment will become zero. Now, if we apply certain external magnetic field, so all the other domains which are in some other direction, either they will rotate and align itself in the direction, or some will jump and from other domain to come inside in that domain which is in the direction of external magnetic field. तो जिस डोमेन का डायरेक्शन, डोमेन के अंदर डाइपोल मोमेंट का डायरेक्शन एक्सटर्नल मैग्नेटिक फील्ड के डायरेक्शन में है, उसमें और एटम्स ऐड होने लग जाएंगे, तो 10 टू द पावर 11 से 10 टू द पावर 19, 10 टू द पावर 20 के ऑर्डर का डोमेन बन जाएगा. ऑल द अदर डोमेन्स कॉन्ट्रैक्ट इन साइज, बाकी सबका जो साइन था, डायरेक्शन था, दैट विल बी, साइज विल बी वेरी वेरी रिड्यूस्ड. Almost the entire volume of that material will have a domain or dipole moment in the same direction as external magnetic field. So when external magnetic field is applied, when external magnetic field is applied, the domain align themselves in the direction of external magnetic field, either by orientation, by rotation, or by using the transfer form one by stretching their boundary. When external magnetic field B naught is applied, राइट. सो व्हेन एक्सटर्नल फील्ड इज अप्लाइड, तो बाकी सारे जो डोमेन्स हैं वो अपने को रोटेट करके एक्सटर्नल फील्ड की डायरेक्शन में अलाइन करते हैं ताकि वो स्टेबल हो जाए. एंड बिकॉज ऑफ द डोमेन्स अलाइनिंग, सो एक डोमेन में ऑलरेडी 10 टू द पावर 11 थे, इट विल बी 10 टू द पावर 15, 16 का number of electrons having the same direction. So a very very strong magnetic dipole moment is created which produces very strong magnetic field. External magnetic field is applied, the domains, just one domain, the domains align themselves in the direction of external magnetic field. For the same reason, क्योंकि external field में आएंगे तो stable हो जाएंगे, और stable हो जाएंगे तो potential energy will be minimum in the direction of external magnetic field. Either by rotation or by displacement of its boundary. दो फिनोमेना हो सकते हैं, या तो वो रोटेट होकर उस डायरेक्शन में आ जाएगा, या फिर अपने बाउंड्री चेंज कर लेगा बाय डिस्प्लेसमेंट ऑफ डोमेन बाउंड्री. सो अल्टीमेटली उस पूरे ही मटेरियल के अंदर एक मैग्नेटिक बिहेवियर आ जाएगा एंड अ वेरी स्ट्रॉन्ग मैग्नेटाइजेशन अकर्स। मैग्नेटाइजेशन मतलब वो वेक्टर जो हमने लिखा था, डाइपोल मोमेंट पर यूनिट वॉल्यूम, दैट वन, strong magnetization occurs. Because of that, because of that, it has very high magnetic field potential. So for any ferromagnetic substance, इसकी मैग्नेटाइज्ड होने की प्रॉपर्टी बहुत ज्यादा है. दैट मींस chi is very strong. It will be of the order of 500, 600, thousands. Relative permeability is also greater than 1. Permeability is greater than permeability of space. B is greater than permeability of net magnetic field is quite larger than the magnetic field applied or magnetic field. So ferromagnetic substance में हम जैसे कोई material को magnetic substance में रखते हैं, magnetic field में रखते हैं. If it is a ferromagnetic substance, it becomes very strongly magnetized and very strong magnetic field is produced inside, as well as the net magnetic field is also very strong. So for the ferromagnetic material, if we check the property, why there is a domain formation? Because of some specific geometry, crystal geometry. Why there is a domain alignment? Either by rotation, because all the domains, all the dipoles want to be in the same direction. So properties of ferromagnetic substances, most of it is similar to paramagnetic, but a magnetic field strength will be very high. And some are the properties specific to the ferromagnetic material. So first is it increases the magnetic field. So वो हम ऊपर definition में लिख चुके हैं. When placed in the external magnetic field, uniform magnetic field, almost all of the magnetic field lines will pass through the ferromagnetic material, and the reason is because it is very strongly magnetized. So in a way हम ऐसा भी बोल सकते हैं, almost सारी के सारी magnetic field line इसके अंदर से ही पास होगी. Almost all of the magnetic field lines will pass through inside of the ferromagnetic material. So ऐसा ही कुछ पैरामैग्नेटिक में था. पैरामैग्नेटिक में थोड़ी सी इंक्रीज की थी, इसने बहुत ज्यादा इंक्रीज की थी. नेक्स्ट, पैरामैग्नेटिक सब्सटेंस नॉन यूनिफॉर्म इलेक्ट्रिक मैग्नेटिक फील्ड में स्ट्रॉन्ग मैग्नेटिक फील्ड की तरफ जाते हैं. यहाँ पर अगर कोई भी नॉन यूनिफॉर्म मैग्नेटिक फील्ड है और कोई हमने पैरामैग्नेटिक सॉरी फेरोमैग्नेटिक सब्सटेंस रख दिया, लाइक सपोज दिस इज आयरन रॉड. तो आयरन रॉड अपने आप को हमेशा एक्सटर्नल फील्ड की डायरेक्शन में ओरिएंट कर लेती है, बिकॉज इट इज फेरोमैग्नेटिक. इट बिकम्स लाइक अ मैग्नेट ओनली. जो प्रॉपर्टी मैग्नेट की होती है, दैट मैग्नेट ओरिएंट इटसेल्फ विद द डायरेक्शन ऑफ एक्सटर्नल फील्ड, वही प्रॉपर्टी इस आयरन रॉड की हो जाएगी, क्योंकि इसके अंदर मैग्नेटाइजेशन की वजह से ये एक ऑलमोस्ट लाइक अ मैग्नेट बन गया है. बट दिस मैग्नेट इज टेम्पररी, नॉट अ परमानेंट, बिकॉज मैग्नेटिक फील्ड के प्रेजेंस में ही रहेगा. मैग्नेटिक फील्ड ऑफ कर देंगे, then the magnetic property will be gone. Okay. Understood ये last statement? किसी भी नॉन यूनिफॉर्म मैग्नेटिक फील्ड में पैरामैग्नेटिक सब्सटेंस थोड़ा बहुत मूव करता है. आयरन की बड़ी सी रॉड भी अपने आप को एक्सटर्नल फील्ड की डायरेक्शन में अलाइन कर देती है. थर्ड, बाकी सारी प्रॉपर्टीज तो सेम है, हम सिर्फ टेम्परेचर वाला देख लेते हैं. टेम्परेचर एंड देयर आर फ्यू मोर. अगर हम किसी भी फेरोमैग्नेटिक सब्सटेंस का टेम्परेचर बढ़ाते हैं, तो डोमेन जो रोटेट होके आए थे वो फिर से वापस बिकॉज ऑफ एनर्जी it start again misaligning and orientation जो सेम डायरेक्शन में था वो फिर से ब्रेक हो जाएगा. On increasing temperature, the alignment or the domain formation breaks, and again it will be individual domains, and at a certain particular temperature even all the atoms of the domain also become free from each other, and they will be again like individual atoms free for any random direction orientation. अंडरस्टूड दैट टू फिनोमेना, पहले जो डाइपोल्स एक पूरा सिंगल अलाइन हुआ था वो पहले फिर से रोटेट होना स्टार्ट हो जाएगा, ये सारे डाइपोल्स, फिर वो वापस अपने डोमेन में ब्रेक होकर जाएंगे और डोमेन में से फिर सारे एटम्स फ्री हो जाएंगे ऑन इंक्रीजिंग टेम्परेचर ऑफ अ फेरोमैग्नेटिक सब्सटेंस.
Sir, can you move to the previous page?
Yes.
Sir,
Done. On increasing temperature of any ferromagnetic substance, what happens is the domain alignment breaks. First step is domain alignment, second step is domain formation, and third step is all the electrons again start being randomized. So on increasing temperature T of a ferromagnetic substance, the domain alignment breaks. Domain alignment breaks, and at a certain temperature, the domain breaks into individual atoms. That means now each electron or each atom is free to orient in any direction. Individual atom. So domain ही वो चीज थी जिससे ये पैरामैग्नेटिक से डिफरेंट था, बिकॉज पैरामैग्नेटिक में तो अलाइनमेंट होता ही है, यहाँ पर अलाइनमेंट बहुत फास्ट हो जाता है और बहुत सारे एटम्स का था बिकॉज ऑफ already formed domain. So agar on increasing temperature ferromagnetic substance domain alignment breaks, and at a certain temperature domain break into individual atom, and the material start behaving as paramagnetic. तो जो फेरोमैग्नेटिक सब्सटेंस है वो एक टेम्परेचर के बाद पैरामैग्नेटिक जैसा ही बिहेव करेगा, starts behaving as paramagnetic substance. Domain breaks into individual atoms and material start behaving as paramagnetic substance. This temperature is called Curie temperature. फेरोमैग्नेटिक सब्सटेंस फेरोमैग्नेटिक होता है केवल क्यूरी टेम्परेचर के नीचे, क्यूरी टेम्परेचर से ऊपर जाएंगे देन द फेरोमैग्नेटिक सब्सटेंस कन्वर्ट्स इनटू पैरामैग्नेटिक. द बिहेवियर वाइज मैग्नेटिक बिहेवियर वाइज, ऐसा नहीं कि वो आयरन है तो कॉपर में चेंज हो जाएगा. It will remain iron only, but because of the field effect, that will change. This is represented as Curie-Weiss law, that magnetic susceptibility of ferromagnetic substance decreases with temperature, but not as fast. Initially it is slow. This is still it is like a paramagnetic substance. Beyond this Curie temperature, it is inversely proportional to the temperature rise above the Curie temperature. So Curie-Weiss law is that above T is equal to Tc, above T is greater than Tc, susceptibility is inversely proportional to temperature rise above the Curie temperature. उसके पहले कुछ parabolically decrease, and beyond TC it is again like exponential decrease. I is proportional to T minus TC. On increasing temperature, susceptibility will decrease, and that will be inversely proportional to temperature rise above Curie temperature. Right? So that's the Curie temperature. इसके अलावा और कौन सी प्रॉपर्टीज डिफरेंट होती हैं? लाइक पैरामैग्नेटिक सब्सटेंस तो थोड़े से मैग्नेटाइज होते हैं, फेरोमैग्नेटिक सब्सटेंस मैग्नेटाइज तो होते जाते हैं, बट इट विल सैचुरेट. सैचुरेट मतलब एक लिमिट तक की मैग्नेटिक फील्ड बढ़ेगी, उसके बाद बाहर की फील्ड को कितना भी बढ़ाओ, the magnetic field will not increase beyond a certain time.
Could you go back to the previous slide?
Yes. So basically on this graph, less than T is T less than TC. This graph is, while it is ferromagnetic property, so change हो जाता है, मतलब iron copper में बदल नहीं जाता. Iron is still iron only, but the magnetic behavior towards the external magnetic field, that will change beyond the Curie temperature, Curie point. Done?
Yes, sir. Yes, sir.
Right, so the ferromagnetic material shows saturation. The magnetic field in ferromagnetic material gets saturated beyond a certain temperature. Certain external field in ferromagnetic material gets saturated. फील्ड बढ़ाएंगे इनिशियली एक्सटर्नल वाली, तो मैग्नेटिक फील्ड मैग्नेट के अंदर भी बढ़ेगी, but beyond a certain point, on even on increasing the external field, the magnetic field inside the ferromagnetic material will not change. What is the reason for it? Why it gets saturated? Any idea? Yes, why it gets saturated? Bharat, why the magnetic field inside ferromagnetic gets saturated? Any guess?
Because as we've already mentioned that they are strongly magnetized. Probably that could be the reason.
They are strongly magnetized. That's the reason they are having very strong magnetic field when we apply external field. But if we increase external field, initially it increases, but after a certain time it does not show further increase. That's the meaning of saturation. What is the explanation of being saturated? Why it gets saturated? Anyone? What could be the reason why it gets saturated? Because?
So because the permanent magnets change the direction of magnetization.
If you change the magnetization, then it will be changing the magnetic field. Well, what this statement is saying, that they become magnetized in one particular direction, and then there is no further change. It gets saturated at that value. So the reason here is because we say there is an external field causes the domain rotation and alignment and the size increase. So with increase in the external field, the domain more and more domain will be orienting themselves in the direction of external field. And at a particular temperature, 100% domain alignment occur. Beyond that, whatsoever increase in external field cannot cause any further increase in magnetic field because there is no more domain left. It gets saturated because 100% domain gets aligned. After that, there is no more domain, no more atom left to align itself in the direction of external field. So even when you increase the external field, there will not be any change. Got it? Understood the logic? Hopefully. Next property. Ferromagnetic substance retains some of its magnetic property even after external field is removed. This property is called hysteresis. Hysteresis means it the value of magnetic field present inside depends upon the history. That means if it is initially magnetized or not, that will decide whether the iron has some magnetic behavior inside present or not. So ferromagnetic substance explanation is that there are domain formation because the domain the behavior is different from the ferromagnetic, but once then it is done, all the magnet gets all the material get permanent saturated 100% in the presence of external magnetic field. And
So we can't hear you.
what is now?
So you're barely audible. Your voice keeps some faltering off.
Is it the network issue or the volume issue?
So volume, I
The
think.
volume. Okay. So I just said that the ferromagnetic material retains some of its magnetic field. Now it's better.
Yes, sir.
Magnetic field retains some of the magnetic field by a property called this property is called hysteresis. That the value present the magnetic field inside a ferromagnetic material depends upon its history, whether it was previously magnetized or not. That will decide the value of magnetic field present. Which we also represent in the hysteresis loop. What was H? Bharat, what was H? You remember? What what H is called and what is the value formula for H? Bharat?
Yes, sir. Sir, I'm not able to. Sir, H in magnetism. Planck's constant, you mean?
No, beta, no capital H. I'm asking this one only.
Magnetic intensity.
Of what? Magnetic intensity of external field. So it is
Sir,
defined
can you
as
go
it
to the
was the
previous page for a minute?
yes. So now we'll be discussing the hysteresis loop or curve hysteresis curve for an iron or for the ferromagnetic material. When we apply some external field, there will be different type of magnetization present depending upon yes, we are. हो गया भरत? Done.
Yes, sir.
H is the magnetic intensity or magnetic intensity of external field. Formula was B naught by mu naught. So now we are analyzing this graph of B versus H for some ferromagnetic material. So let's take iron. So this is some soft iron rod. So we have to put it into some external magnetic field. That magnetic field will apply H. Because of that H, there will be some magnetic field developed, and that magnetic field is plotted on the y-axis. So what we do is we put it inside a solenoid. That iron rod is put inside a solenoid having n number of turns per unit length, small n, with current as I. So since now this iron is present in the axis or inside along solenoid, the long solenoid magnetic field is almost constant, which is mu naught times Ni. Inside there is a magnetic field, and that magnetic field will act as external magnetic field. This magnetic field produced by the current passed in the solenoid behaves like the external magnetic field. So I and the number of turns per unit length is small n. So since current is I, number of turns is small n, B naught is equal to mu naught n I divided by mu naught. So H will be n times I. Which means अगर हमें इंटेंसिटी बढ़ानी एक्सटर्नल फील्ड की तो बस हम इस लूप में करंट बढ़ाते जाएंगे और डायरेक्शन चेंज करनी एक्सटर्नल फील्ड की, देन वी विल चेंज द डायरेक्शन. इसमें कुछ न्यूमेरिकल्स हैं एसएल में भी एंड एक आधे बार बोर्ड में आए हुए हैं पहले. Now if we have to check this variation, we increase the current in this solenoid, that will increase the intensity, and because intensity is increasing, so there will be increase in the magnetic field also according to Magnetism. अब अगर हमने फील्ड बढ़ाना स्टार्ट की तो क्या होगा? इनिशियली व्हेन देयर वाज नो मैग्नेटिक फील्ड, देयर वाज नो मैग्नेटाइजेशन, magnet was not having any magnetic, iron does not have any magnetic property. We increases, magnetic field increases, and at a certain level it is saturated. Now beyond this point, even if we increase the external magnetic intensity, B is not going to increase because 100% alignment has already taken place. Opposite, so suppose हम current को 0 से लेके और 10 एम्पियर तक increase करते जा रहे हैं 0 1 2 3 4 5 6 10. Now we are again decreasing the current back to 0 again. So from 10 9 8 7 6 back to 0. When it is made 10 to 9, the magnetic field that the substance has is greater than the magnetic field that it has while at the time of magnetization. This is also called as hysteresis, that this is not following the same path, following a different path for magnetization and demagnetization. Magnetize करने के लिए हम current increase कर रहे थे, demagnetize करने के लिए हम current decrease कर रहे हैं.
Can you repeat this?
Yes. You understood this, that H is directly proportional to current,
Yes, sir.
and the external magnetic field, this we derived last class, V is equal to mu times H. So the total field produced will be directly proportional to H. That was the magnetization mathematics that we did.
Yes, sir.
Mu is mu naught times mu R. To increase the external magnetic field, we just increase the current. We started from 0. Initially magnetic field 0, intensity 0, magnetic field 0. We increases the current, magnetic field is increasing, and at a certain temperature it will be completely saturated. Arnav,
I can't hear you.
can't hear me. Why?
Now I can hear you.
Hello? Now?
So I can hear you now.
Okay. Now I'm using Bluetooth. Maybe its position will be changing. My position, I'm not very sure it's a new one. Because of increase in the external magnetic intensity, magnetic field inside iron is increasing till it gets saturated. This is clear.
Yes, sir.
Now current is decreased. It should have been following the same value as before. If initially at the 9 ampere it has 10 Tesla, while coming back at 9 ampere it should have 10 Tesla, but instead of 10 it shows 12 or 13 Tesla, means it has already stored some of the magnetic field inside. It is not going back to the same value as before as it was during the magnetization. Understood?
Yes, sir.
When even the external magnetic field is completely switched off, the current is made 0. The material should have been demagnetized, but instead some of the magnetic field is still present. That length is represented here as OA. This is called retentivity of material. Retentivity is some property that is depending upon the material. It will be the magnetic field stored inside that material even when the external magnetic field is switched off. And because of this retentivity or because of this remanence, the iron is still behaving like a magnet for a short period of time when it was kept in contact with magnet for some time. Now, if you want it to be back as a normal magnet without any magnetic property, then what we have to do, we have to demagnetize it forcibly. Forcibly means now we have to reverse the direction of external current so that the external magnetic intensity is reversed, and at certain negative magnetic intensity value, external field, the field inside that material is completely demagnetized. It becomes 0 now. These two steps clear. What is the retentivity?
Yes,
External
sir.
current that was increased, now it is back to 0. Still there is some magnetic field left. That's called retentivity. Now to completely demagnetize it, we have to use opposite direction magnetic field, and the amount of magnetic field that is required to provide the completely demagnetize it is called magnetic intensity vector, and that length O to C, that length represent, that's called coercivity. O to C length is called coercivity. So these two are some constant for a material and which decides which ferromagnetic material will be suitable for what purpose. Coercivity is that negative intensity which on which the magnet or the material is completely demagnetized. Correct? Increase the current now in opposite direction. Again, similar thing. It increases, gets saturated. Again, complete opposite direction. Again, when it is reduced, made zero. Still, some of the magnetic field is still left. So in this way, this makes one complete cycle of magnetization and demagnetization. Started increasing the current in this solenoid, that increases the intensity, which increases the magnetic field till saturation. Once it is saturated, once it is saturated, once it is saturated, then after that we reduce the current to reduce the external intensity, but magnetic field does not reduce in the same proportion. Some of the magnetic field is retained. When external field is gone, even though it is having some of the magnetic field present, that's called retentivity. So depending upon what is the purpose of that material, we require either high retentivity or low retentivity. But one thing is for sure that the magnet, the material, to make it as a normal magnet, there's some energy is wasted. Energy corresponding to OC, so which is also directly proportional to area. Area under BH curve inside represents some kind of energy loss in the form of heat during a cycle of magnetization and demagnetization. एरिया अंडर बेस कर्व क्या रिप्रेजेंट करता है? हीट लॉस और एनर्जी लॉस पर यूनिट वॉल्यूम पर साइकिल पर यूनिट टाइम. हीट लॉस पर यूनिट वॉल्यूम पर साइकिल पर यूनिट टाइम. साइकिल का मतलब जैसे ये एक साइकिल है, ऐसे अगर कोई हमने बड़ी सी एसी करंट लगा दी अगर, तो एसी की फ्रीक्वेंसी होती है 50 हर्ट्ज, यानी वो एक सेकंड में 50 साइकिल होगी. there will be 50 cycles, so there will be heat loss. The area bounded by the material, sorry, area bounded by the BH curve represent the amount of heat loss per unit volume per unit cycle per unit time. So इसकी जो unit होगी, that unit will be joule per meter cube per second per cycle inverse. Okay, so hysteresis loop का area में Yeah, I got disconnected. Am I audible now?
Yes, sir.
Yes.
Okay. So ये hysteresis को समझ में आ रहा है BH curve. This is very important for the theoretical as well as some numericals. So जब हम magnetic field बढ़ाते हैं external वाली by increasing the current, magnetic field inside the solenoid, inside the iron material will also increase till it gets saturated. After it gets saturated, even if we reduce the current, the magnetic field will not be reduced by the same amount. It will be slightly more than the previous value. That is the word hysteresis mean. Hysteresis is strictly related. Area will depend upon the coercivity and retentivity, and that area will decide how much is heat lost per unit cycle, per unit volume, per unit time. So we require high retentivity or low retentivity, high coercivity or low coercivity. That depends upon the purpose where it is being used. So soft iron and hard iron. Soft iron is the iron that is called wrought iron also in chemistry. It is having a very low retentivity and low coercivity, so very low area. This is for soft iron. So in a soft iron, this is for a soft iron. This is fit for electromagnet because it has low retentivity and low coercivity. Electromagnets are formed by soft iron because electromagnet properties that as long as there is a current, it should be having, it should be becoming a magnet. As the external current is switched off, it should be demagnetized. So soft iron is preferred for electromagnet. If we have to make a permanent magnet, how do we make a permanent magnet? किसी भी ferromagnetic material like especially the alloys, alnico alloys, उसके साथ उसको किसी magnetic field में बहुत time तक रख देते हैं, 1 month or so. You keep it in tied with a magnet. alnico या किसी भी ऐसे material को ferromagnetic material के alloy को किसी भी magnet के साथ बांध के महीने भर के लिए छोड़ देते हैं. That will make it a very strong magnet because this magnetized retentivity will increase. So hard iron. What is hard iron, Arnav?
So I don't know.
What is steel? I mean, how iron is converted into steel?
So I have no idea.
Okay. Anyone? How iron converts into steel? Renee?
Yes, sir.
Iron और steel में क्या difference है? मतलब composition wise, how iron converts into steel? Yes.
तो स्टील एलॉय होता है.
Steel alloy होता है. Very good. But कैसे बनता है वो?
तो शायद
How it is-
कार्बन ऐड करते हैं शायद.
Okay. किस में ऐड करते हैं?
वो याद नहीं.
Iron.
आयरन.
आयरन में आयरन प्लस कार्बन इज स्टील. उसमें और भी बहुत सारी चीजें मिलाते हैं, वेनेडियम फॉर स्टेनलेस स्टील एंड डिफरेंट टाइप ऑफ स्टील. हाई रिटेंटिविटी एंड हाई कोर्सिविटी, सो इट इज स्टील और हार्ड आयरन. दिस इज यूज्ड फॉर परमानेंट मैग्नेट. कोर्सिविटी हाई क्यों होनी चाहिए? क्योंकि आसपास कोई छोटी मोटी अगर मैग्नेटिक फील्ड गलती से आ भी जाती है तो उसको डिमैग्नेटाइज ना कर दे. So coercivity is that opposite magnetic intensity required to completely demagnetize. So इसीलिए जब भी हम किसी AC सर्किट में कहीं पर भी आयरन का कुछ भी हमें यूज करना होता है, any core or anything we have to use, we always use it of soft iron. The core inside transformer, the core inside moving coil, galvanometer, they all are always used of soft iron so that during that AC supply, during the cycle of magnetization and demagnetization, there should not be much heat loss. स्टील या फिर हार्ड आयरन लेंगे तो उसमें एरिया ज्यादा है, मतलब ज्यादा हीट लॉस हो रही है, और ज्यादा हीट लॉस होगी तो इट विल बी getting heated over a period of time. right? So soft iron, hot iron, soft iron इसके अलावा और हम permanent magnets जो बनाते हैं, that permanent magnet is specific alloys which has even very high. If suppose a particular material, some ferromagnetic material is kept in a AC supply, with each cycle its retentivity will increase. पहले इसने थोड़ी सी मैग्नेटिक फील्ड अपने अंदर स्टोर की थी, अगली बार और ज्यादा, अगली बार और ज्यादा, एंड सो ऑन. सो इट्स सैचुरेशन वैल्यू तो सेम ही रहेगी, बट द ओवरऑल magnetic intensity that it has stored inside, that will keep on increasing. So size will be increasing, therefore heat loss will also be increasing. Understood? पहले इस साइकिल में उसने थोड़ी सी रिटेन रखी, अगली बार उससे और ज्यादा, अगली बार उसको और इंक्रीज किया. So ऐसे करते करते दिस साइज और द हीट लॉस विल आल्सो बी इंक्रीज्ड if it is used in an AC, and that's why we always use a laminated soft iron core to reduce the heat loss or reduce the energy loss. Correct? बेटा ये समझ में आ रहा है क्या क्या था ये?
से फिजिक्स एक्सप्लेन कर दो.
AC supply में, like suppose in the household AC, in first cycle it had some amount of magnetic field retained inside, maybe 0.1 Tesla. अगली बार वो 0.1 से 0.1 और ऐड हो गया, 0.2, 0.3, 0.4. So the retentivity is increasing, coercivity is increasing. साइज अब वो 0.2 टेस्ला जब हो जाएगा सेकंड साइकिल में, तो उसको डीमैग्नेटाइज करने के लिए भी हमें ज्यादा कोर्सिविटी लगानी पड़ेगी. सो विद यूजेस द कोर्सिविटी एज वेल एज रिटेंटिविटी विल बी इंक्रीज्ड, एंड देयरफॉर मोर अमाउंट ऑफ हीट विल बी लॉस्ट. सो इसीलिए कभी भी हम एसी सप्लाई में डायरेक्ट एज अ थिक आयरन कोर यूज नहीं करते. ऑलवेज वी हैव टू यूज लैमिनेटेड सॉफ्ट आयरन कोर. Laminated soft iron core is used in the transformer. Understood? Laminated का मतलब क्या होता है कि एक बल्क पीस ना यूज करके one sheet then another sheet और उनके बीच में हम एक इंसुलेशन लगा देते हैं, so that उसके बीच में बहुत ज्यादा strong magnetization ना हो पाए. It will not be a strong magnetic field, strong current, and there should not be much heat loss. Understood?
Yes, sir.
Fine. So that is the, I think all the concepts of this particular chapter we have done. The few things that we left, maybe Mesner effect and some theoretical concept that we can discuss. So in the diamagnetism, we use that all the materials have diamagnetic property. This also we discussed. Diamagnetism is a universal property. Why it is a universal property? Because सबके अंदर paired electron तो होते ही हैं. केवल लास्ट में जाके लास्ट शेल में एक आधा अनपेयर्ड इलेक्ट्रॉन बचता है, जिसकी वजह से पैरामैग्नेटिज्म डोमिनेट्स ओवर द डायमैग्नेटिक बिहेवियर. जिसमें नहीं होते हैं उनमें सारे के सारे डायमैग्नेटिक. सो डायमैग्नेटिज्म इज यूनिवर्सल प्रॉपर्टी. डायमैग्नेटिज्म क्या होता है? एक्सटर्नल मैग्नेटिक फील्ड को थोड़ा कम कर देना बिकॉज ऑफ बीइंग अलाइंड इन अपोजिट टू द एक्सटर्नल मैग्नेटिक फील्ड. Those substances which gets magnetized opposite to the external field and reduces the magnetic field by a small amount, those are called diamagnetic. अब आते हैं हम superconductors पे. What is superconductor, Meher?
So
Superconductors?
can I tell the definition of a superconductor?
No, let Meher first try. Meher, what is superconductor? Meher? Aradhya, what is superconductor? Aradhya, what is superconductor? Okay, no idea. Superconductors क्या होता है? चलो भरत आप ही बताओ. What is superconductors? भरत.
Superconductors are materials which at sufficiently low temperatures stop resisting the flow of current.
What? Stop resisting the flow of stop.
Means
Stop.
they don't stop the flow of current. Means R is equal to 0 ohms almost.
R is equal to 0. Okay, that's what you want to say. Fine. Superconductors are all any conductor when it is very close to 0 Kelvin or very low temperature. It all conductors close to 0 Kelvin. So like for iron it is 10 Kelvin, for lead it is 8 Kelvin. All conductors close to 0 Kelvin temperature becomes superconductor. That means very negligibly small resistance, almost zero resistance. That means once current is established, it will be for a very long period of time. It will not be lost. Current that is established for once, it will be there for a very long period of time. Mesner effect क्या बोलता है? All superconductors are perfect diamagnetic substance. All superconductors exhibit perfect diamagnetism. What was diamagnetism? External magnetic field को oppose करना, थोड़ा सा कम करना. Perfect diamagnetism का मतलब external magnetic field को खत्म कर देना. So all the superconductors inside there is no magnetic field. बाहर कितनी भी magnetic field क्यों ना हो, the susceptibility of superconductor is conducting material becomes -1. When it is -1, that means mu r is 0, V will be 0. So बाहर कोई भी field हो, inside superconductors there will never be a magnetic field, or in fact reverse, it is repelled from a magnetic field. I mean, another application is diamagnetic substances are slightly repelled, so it is also repelled from the external magnetic field, which causes a repulsion, and that repulsion is a very strong repulsion which is used even in the magnetic levitation of bullet trains. The magnetic levitation कहाँ use करते हैं? The bullet train, they move at such a high speed that they cannot run on a track. They are slightly above the track, so that there is not much friction. So जितने भी superconducting materials हैं वो external magnetic field को strongly repel करते हैं, अपने अंदर net magnetic field zero कर देते हैं, and that is used in the magnetic levitation. Superconductors are used in the bullet trains also. Understood? थोड़ा बहुत देख लेते हैं. Let's show that if it is available here. The magnetic levitation by superconductors. Okay. Something like this. So because it is a diamagnetic substance is Diamagnetic substance is understood?
Yes, sir.
Fine. So now this chapter is done. Mesner effect is just a practical concept. So how superconductors work? Superconductors के अंदर there is no movement of electron. Electrons do not move, and that's why there is no collision. There is no collision. There is no collision, therefore there is no heat loss, and therefore resistance is zero. And as a result, current established will be going without much loss of energy. Okay, so done. I think that's it in this chapter. Next chapter is electromagnetic induction. We have some 5-6 minutes left. We can continue. If you have any doubt, you can ask. Diamagnetic, ferromagnetic, paramagnetic substance. Paramagnetic are those which are slightly magnetized, increases magnetic field by a small amount. Diamagnetic, which is oppositely magnetized, decreases the magnetic field by a small amount. Ferromagnetic are very, very strongly magnetized, and it kind of increases magnetic field by at least 1,000 times. Harder and we understood, and there are a few numericals, but not very relevant for the school now. So I am leaving. Maybe in the Friday class we can do a few to understand how to calculate the heat loss. Okay, right. So electromagnetic induction. That's the next chapter. In the first term, AC is there. EM wave is also there in first wave? I don't think so.
EM wave comes in the second term.
Second term, right. Okay. Electromagnetic induction. So induction is a phenomena that means inducing something. So this you have done a little bit in class 10th. External magnetic field causes some kind of electric current to appear. But before that, we have to understand one more term, because induction is defined in terms of the magnetic flux. So like electric flux was electric number of electric field lines passing perpendicularly through an area. Similarly, the magnetic flux is the total number of magnetic field lines. Total number of magnetic field lines passing perpendicularly through an area is defined as magnetic flux. The total, this is chapter number 6. Total number of magnetic field lines passing perpendicularly through an area is defined as electromagnetic induction. Now, in a closed loop, it is always zero, but this is not a closed loop. This is one single loop. We saw that Gauss law for magnetism was zero. Now, this is only for one single particular area. It is not for a closed loop. So if this is a magnetic field, some uniform magnetic field, which is not obviously for a magnet, might be inside of a solenoid, or and there is a loop placed at an angle theta with respect to magnetic field. If angle between them is theta, then the magnetic flux will be defined as similar to electric flux. That was E dot A, here it is B dot A. Angle between B and A is theta, so magnetic flux will be B times A cos theta. That's the electric field. Flux is, so to precise, we should write phi B, but by the unit also we can understand. It is Tesla into meter square, and another name for the Tesla meter square is VAIBHAV. The total number of magnetic field lines passing perpendicularly through an area. Got it? And that's how the magnetic flux is also. So A cos theta is what? A cos theta is also the perpendicular area. Perpendicular to what? Perpendicular to magnetic field line, which we call as projection area in the electric field. The electric field projection area is that area which is perpendicular to the field line. So magnetic field is also called as, in the same term, if it is a uniform magnetic field, then B dot A. If it is a non-uniform magnetic field, then we have to integrate by taking a small area dA on that surface, and then we integrate. In non-uniform magnetic field, the total magnetic flux will be integral of B dot dA. We will not put here close symbol, like circle symbol that we use for electric flux in the Gauss law, because if we apply that close symbol, that means we are doing the integration on a closed loop, and as per the Gauss law of magnetism, for any closed loop, the total magnetic flux will always be zero, because the field lines are always in the form of closed loop. So if it is entering from one side to a loop surface, it will be leaving from the other side also. As a result, it will cancel out. Right? Okay, this is the Gauss law for magnetism. That's we have already done in the previous chapter. So uniform magnetic field, B dot A, like BA cos theta, similar to E dot A, EA cos theta. And if it is a non-uniform magnetic field, then we have to consider a small surface dA, integrate B dot dA over its entire surface. Magnetic field, another name for magnetic field is, because if it is perpendicular, phi is equal to B into A. If there is a surface area A kept in the magnetic field, then the flux is perpendicularly. So there is another name for magnetic field. Magnetic field is also defined as flux passing per unit area through a perpendicular surface, and therefore it is called magnetic flux density. One more name for magnetic field is, it is also called as magnetic flux density. That means flux passing per unit area, or Weber per meter square is another unit for magnetic flux. Right? Okay.
Yes, sir.
So, okay. I think we'll continue from here in the next class Thursday. So now we'll try to slightly increase the speed. By the end of September, we are supposed to finish this whole complete chapter of syllabus of term 1. Right? Okay. Thank you.
Thank you, sir.
Thank you, sir.